I, Sasibhushan Tiwari, welcome you all. Today we are going to take up a question that is really hard to categorize to which chapter it actually belongs to. I leave it as an exercise for my viewers to put it in chapter of their choice. Do write it in your the comment section. But leaving that aside, the question really tests your general awareness of physics. It is not based on any intricate physics law, or it does not involve hard mathematics, but still it tests you on your ability to apply the basics that you have learned. So let us have a look at our today's question. I will read it out for you. Take a pause, think over it, give it a try on your own. Here is your question. Consider a light uniform metal rod AB of length L, which is rigidly fixed at end A. The rod is horizontal. The free end of the rod is pushed down slowly by applying a gradually increasing vertical force. At any stage, the force is proportional to the vertical displacement of the end B. That is very critical statement. When the vertical displacement of the end B was x naught, much less than L, a weight W was hooked to the end and the rod remained in that state after the applied force was removed. Great. Consider the shape of the rod to be an arc of a circle of radius r in this state. The stored elastic energy represented by U in this state of the rod is proportional to its length L and inversely proportional to square of its radius of curvature. We can write the elastic potential energy as some constant C into L by R square, where C is given by W L cube divided by N x naught. The value of N will be, N is an integer, its value can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to figure out what is the correct value of N. I will get out of the screen for a moment so that you can capture the question properly and do give it a try. It is worth giving it a try. After that, you can listen to me and my solution. Look at my solution. Here I am proceeding with my solution. The question says that the rod is basically horizontal. I'll just represent it by line. Rod is basically horizontal. Its end A is fixed, B is free. The rod is a light rod, it does not have any weight. Now you apply a vertical force like this and push the end B of the rod downward so that it gets bent. The question says that this force F, required force F, is proportional to displacement of point B, vertical displacement of point B. If you push this end B down by x, the force is proportional to this distance x. The more you push it down, higher is the force. The rod is being deformed slowly, means at any point in time, there is no kinetic energy kind of thing. At any point in time, it is in equilibrium. The force is being increased gradually so that rod bends slowly actually, and the force is proportional to x. In the final state, the displacement of end B is x naught, and therefore the rod gets bent like this. Obviously, this diagram is correct only if we assume that this x naught is much less than L, which is given in the question. If x is really large, then this point of the rod will be somewhere here. But under the given assumption in the question, it is quite fine to assume that point B is just here. With respect to L, the displacement of point B is extremely small. In real life, for a real rod, which will have some mass also, this curve is not exactly arc of a circle, but as a kind of estimation problem, The question says that approximate it as an arc of a circle. Let us assume that radius of curvature of this arc is r. So, if I assume that radius of curvature of this arc is r, then immediately you can see that this length is r minus x naught, right. The rod has been, the end B has been pushed down by distance x naught. So, this length is r minus x naught, this is almost L, and this is r. So, just by using Pythagoras theorem, I can write r minus x naught whole square plus L square is actually equal to r square. So, this becomes r square plus x naught square minus 2r x naught plus L square is equal to r square. So, this r square cancels out, and moreover I am allowed to ignore this term, because x naught is a small quantity in front of L, x naught square will be even smaller. So, I am neglecting this term. This becomes minus 2r x naught plus L square is 0, which means radius of curvature is L square by 2x naught. So, I have expressed the radius of curvature of the rod in terms of the length and given quantity x naught. That is my first step. But okay, this is just a step of mathematics. What is the physics involved? The involved physics is also simple to guess. The only force that is performing work here is the force applied by this external agent, pushing the end B of the rod down. There is no weight, there is no change in kinetic energy of the rod. First of all, it is massless, and second, it is being pushed, it is being deformed very slowly. So, there is no question of any kinetic energy term. So, whatever work was done by this force, that gets stored as potential energy of this rod, elastic potential energy in this rod. So, how much work was done by this force? To calculate that, we have to understand that this force is not a constant force, it is a variable force, it is continuously increasing. But the question says approximate it to be growing linearly. The force is growing like this. The question says that force is proportional to this x. So, when this value of x is finally x naught, the force becomes F naught. Wait, F naught is given, isn't it? Can you spot that? F naught is actually W. The question says when the rod is finally bent like this, when the end B is down by x naught, you hang a weight W and remove your force, the rod stays there. What are you doing? You are increasing the force. To bend it more, you have to increase the force. You are increasing the force. Now, hang a weight W and release it. It remains there. It simply means that the end value, the extreme value of the force applied was W. Force was W. So, I replace that force by this weight. So, the rod remains there. So, the value, final value of force was definitely equal to W. And this is a variable force, its work done will be obtained by integration of f dx, but you need not do any kind of integration actually. This integration is obtained by this area of the graph. So, integration f dx is obtained by this area, which is half W x naught. So, work done. This is the amount of potential energy that has been stored in this rod, elastic potential energy. So, this elastic potential energy half W x naught, please don't get confused, I will write it as work done. W is actually the value of this weight, so don't get confused with the symbols. Work done by this force is half W x naught. Now, this work done is stored as elastic potential energy. So, elastic potential energy is half W x naught. Now, according to the question, this elastic potential energy stored in the rod is proportional to length of the rod and inversely proportional to square of radius of curvature of the bed. This is what the question says. So, this is the elastic potential energy and it can be written as C into L by R square. So, what is value of C? C is half W x naught R square L. Do we know the value of R? Yes. Yes. We just calculated it to be L square by 2x naught. So, substitute L square by 2x naught. L square by 2x naught. This is how it will become. If you put R is equal to L square by 2x naught. So, this becomes 1 by 8 W x naught, W L cube by x naught. Am I right? W L cube 8 x naught. And I think this is what was asked in the question. Value of C is W L cube by x naught into n. So, obviously, the right answer is value of n is 8. I hope you enjoyed this session. For more such problems, do subscribe to this channel and wait for the next video. Goodbye.